Okay, continuing with our conversation about randomized experiments, I want to make clear the distinction between random assignment, which is what makes an experiment a randomized experiment, versus random sampling, which is something we talked about a few weeks ago. So if you remember, random sampling uses chance to select a sample from a population. So the goal of random sampling is to select a sample from the population, and that's in order to make an inference back to the population or to make the results generalizable to the population. And that's a different strategy and a different thing than random assignment, which is what we've been talking about, the use of chance to assign subjects or participants to a treatment and a control group. And the aim of random assignment is causal estimation, trying to get a good, cause and effect evidence. So the two strategies are fundamentally different kind of purposes. Random sampling is used to generalize to a population based on a relatively small sample. Random assignment is used to draw causal inferences or make causal conclusions about the effect of a treatment. So let's look at a diagram in the book that helps make this distinction. So this diagram kind of shows the difference. Random sampling is used to draw a sample from a population in order to provide generalizability. Random assignment starts with some sample of people, which may or may not be randomly selected, and it randomly assigns them into treatment group and control group. So if you can imagine sort of a line crossing here, it could be some studies involve just random sampling, right? They just involve a sample drawn from a population. Other studies just involve random assignment. They recruit the sample in some way through volunteers or some convenient sample, students or whatever, and they randomly assign them to treatment and control groups. This diagram shows both together, and it's actually relatively rare that a study includes both random sampling and random assignment. But in some ways, this does provide a kind of ideal if research does make some effort to draw a representative or random sample from a population and then uses that random sample to do a randomized experiment to randomly assign people to treatment and control groups. That in some ways provides the best overall kinds of evidence because you have good causal evidence from the random assignment, and you can generalize that cause and effect evidence back to a larger population because you randomly sampled. But just be careful that most real-world studies involve one or the other, not both. It's relatively rare to have both together. Okay, so that brings up the issue of limited generalizability of randomized experiments. One of the big limitations of a randomized experiment is they're really great at showing cause and effect relationships, but they're often limited in terms of generalizability. And that has to do with limited settings. Sometimes it's only a local group of people who are recruited to be in the participant, a local clinic or a local, university that does the study. They can be in rather limited laboratory settings, which are not like real-world settings, and they have sometimes limited historical time periods, although that's not unique to experiments necessarily. Also, very often experiments rely on volunteers, especially potentially risky or complicated studies. And volunteers may differ from what a random sample would produce. Volunteers may be more interested in research. They may be more interested in the treatment. They may be suffering more from the ailment or whatever. And so there's often a kind of a volunteer bias of sorts in an experiment. Now, the volunteers are randomly assigned, so there's no voluntary bias in the assignment of the treatment, but whether the volunteers represent the larger world is the question of generalizability. And then the treatments themselves may be artificial. Often experiments use sort of simulated driving, or they'll use vignettes rather than real world scenarios, or like even in this pay as you drive insurance scheme, that was sort of a simulated insurance scheme. I don't think that was a real insurance program that actually existed in the Netherlands. So to that extent, the treatments may be artificial, and therefore trying to generalize the results of an experiment to what it would look like if the treatments were real large-scale policies or interventions, that can sometimes be a question. So that's the next point. Really, the treatment may not really resemble a full-scale program. So pilot programs often have more motivated staff or better funding, or they may be simpler or cheaper or whatever. So there's that issue of whether the treatment being tested is really the same as the full-blown treatment that would happen when policies or programs are taken to scale. And then there's also the issue of short-term versus long-run effects. Often experiments tend to look at short-run effects, like this pay-as-you-drive experiment looked at just a few months of driving behavior. It'd be interesting to see how driving behavior would change in the pay-as-you-drive type of insurance over the long term. If the insurance was in place for years, would it have the same effect? So you could imagine possibly a short-term effect, and then people going back to their old ways after that. But that's, again, sometimes often not clear from an experiment. Now, I'm going to talk a little bit about some variations in the design of the experiment. We've looked at rather basic experiments for the most part so far, but there are ways in which experiments can be more complex, and one of those ways is that there can be more than two arms in an experiment. Arms are the various possible treatments or conditions that you can put people in. Basic randomized experiments, as we saw in that diagram, are usually considered with just two arms, a treatment group and a control group, but some experiments have more arms, and we give some examples in the book. But also, even this pay as you drive randomized experiment in the Netherlands, even that actually had three arms. If you recall, essentially one of the treatments didn't work out, but they randomized people to getting sort of a different forms of information on how much money they were saving. And one form of information treated it as a loss, like how much are you losing each month as you exceed the speed limit. Because of this, there's some evidence of loss aversion, that people are maybe more sensitive to losing money than they are to gaining money. And the other condition presented the information about how much people were saving in the term, in they framed it as a gain in like a payback in terms of the money that people were saving each month. But it turned out that didn't really matter too much, and so they ended up folding both of those arms into one treatment group, and then compared that to one control group. But some studies have many arms. You can look at 3 or 4 versions, let's say, of a job training program, and compare that to a control group. So there can be multiple arms to an experiment. Another thing is that there can be one of the reasons to have multiple arms is you might want to vary the dosage of the treatment. And so variations in the design of an experiment can include probing what are called dose-response relationships. So, for example, even in this case of the pay-as-you-drive insurance, so there was a €50 savings potential every month. So we might experiment with that. We could have a smaller version of the program where you only save, let's say, 20 or 25 euros a month, and even a larger version where you could save up to, let's say, 100 euros a month. So one way sometimes experiments are set up is they test not just one treatment versus a control group, but various doses of a treatment, a small cash benefit, a medium cash benefit, and a large cash benefit. And they try to look at the dose response relationship. Like, would people's driving become even safer if you increase the dose of the savings? And yet another way that experiments can vary or become more complex is they can include various factors, and they're sometimes therefore referred to as factorial experiments. So in a sense, this is like testing two treatments at once, as well as the interaction of the treatment. So again, the basic randomized experiments looks at the effect of just one variable, but factors allow us to examine interactions with multiple treatments. So we give the example in the book of a randomized experiment in early childhood nutrition, which looked at the effects of iron and zinc, as well as the combination. So one arm got the zinc, one arm got the iron, another arm got both the iron and the zinc, and a fourth arm got neither, or just a placebo. And so what's great about that kind of design is it can let you know what the individual effects of each treatment are, as well as perhaps the combined effect. And sometimes the combined effect can be greater than the sum of the parts. There can be a positive interaction, which means that, let's say, the two vitamin supplements might together be even more powerful than their separate effects. Or there can actually be negative interactions. There was ways in which treatments can cancel each other out. So that's good to know, and you can probe that with a factorial experiment.